Hi, good afternoon. So, in last lecture we covered the basic design principle of the spillway. Now, we are going to solve a problem based on this to see how the spillway design condition prevails. So, this is the last lecture for drop inlet spillway, and here we are going to cover the design aspect. So, this is the problem statement. So, design an ungated drop inlet, and here we are going to take morning glory spillway kind that will operate under a maximum surcharge head or H0 as 3 meter that can limit the overflow of 56 cubic. Here you determine these are the set of question. So, first we will going to determine the minimum radius of the overflow crest, second the transition shaft radius, and as you remember the minimum we have to design a minimum uniform conduit diameter to consider the 75% of full flow in order to allow the air pass. So, why we consider a 75% of the flow? To allow the losses and to allow the air pass from the conduit from the downstream portal in order to prevent the subatmospheric pressure in the conduit. And based upon this design calculation, so develop a discharge water surface elevation relationship. So, this will be in the form of table, and then you have to assume some set of conditions. So, what are these conditions? So, the horizontal length of the conduit is assumed as 76 meter and the crest elevation is given 30 meter and outlet invert elevation is 16 meter. So, this example design must minimize the overflow crest radius and also subatmospheric pressure along the crest should be tolerated. The conduit portion of the spillway must not flow more than 75% full at the downstream end. So, this should consider this condition. So, now this is the basic diagram. So, here the maximum elevation, since H0 is assumed as 3 meter, So, here it says the H0, the surcharge head is 3 meter and the 30 meter So, 30 meter is the head total head height. So, this leads to the maximum elevation of 33 meters. So, the crest elevation is given as 30 meter and 3 meter is the surcharge head. So, this is, since this is a pipe kind of structure. So, the horizontal diameter is more than the lesser than the vertical diameter here, and this pipe length is 76 meter and invert elevation is given as 16 meter and it is a circular conduit, and this side it is the top portion of the dam. So, this is a profile of this example. Now, so first we assume the radius, and based on this the design problem will follow. The radius of the crest to minimize the subatmospheric pressure that may be tolerated. So, assume the P by Rs is greater than equal to 2. So, now determination of Rs. So, here the radius is given. So, Rs is determined by hit and trial procedure and assuming the values of Rs and computing the corresponding discharge. So, first assume the Rs value as 2 meter. Now, if you assume 2 meter, the ratio between the surcharge head and divided by Rs is now 1.5 meter. So, for this ratio of 1.5 meter and assuming the ratio P by Rs as greater than 2. So, if it is 1.5 meter, So, what is the corresponding value of this coordinate here? So, to determine the coefficient of discharge here. So, the C0 value is 1.35 meter. since this graph is prepared in MKS unit, so we can multiply using a correction factor to convert it into SI unit. So, the conversion factor is nothing but 0.552 here. So, we multiply with this, and then now the discharge from this portion, the inlet is given by using Ware equation. So, C 0 is the discharge coefficient, and since we assume the circular cross section and the outside radius of this cross section. So, this is the perimeter is given by 2 pi r, and this is again head. So, head is assumed as head is given as the surcharge head is 3 meter. So, using this relation, so we get the discharge, the inlet discharge is 48.65. So, here mean to say that P is nothing but the pressure, and the ratio between P by R s, that is the ratio between pressure divided by the radius of the flow is we assume that these curves are obtained at different values of P by R s. Now, our assumed flow is less than, so this one. So, this is the design flow is given the 56 cubic, but our calculated is less than this, the 48 around 48 cubic. So, this is less than the desired outflow. So, again we assume that the radius of the inlet is 2.15 meter. Now, assuming the radius is 2.15 meter, now you again repeat the calculation. So, here if you assume the R s value, the head, so surcharge head is already 3 meter as given in the problem, and now your assumed radius is 2.15. Now, the ratio between them is 1.40. Now, for a given value, so this is divided into 4 different intervals. So, between 1.2 to 1.6. So, here if I go gradually 1.2, to 1.3. So, this point will be nothing but 1.4 and following 1.5 and 1.6. So, from this point to now I am prolonging this line, and the intersect point is locating here. So, now you can see this is 1 and 1.4 and so and 1.8. So, each coordinate is divided into 4 parts. So, how you divide this point? So, to find out the intersection, so you can divide it at different small interval. So, now you can assume that this particular point is 1.46, and now since you have to convert the unit into SI. So, you multiply with this with the conversion factor, that is nothing but 0.552. Now, your C 0 value comes out to be 0.806. Now, this C 0 value you plug into the equation and discharge equation. So, now you obtain the value of discharge is around 56.58 and your design discharge was 56. Now, since it is a little higher side than design discharge. So, this value of R s is acceptable, and you can take the radius of the inlet as 2.15 meter. So, this equation the part you can solve now. Now, the determination of the crest profile. Now, you have an assumed value of 803 and R s is now your 2.15 from earlier steps. So, from this part of the problem. Now, and you assume the ratio between the pressure and the radius of the R s is greater than 2. Now, you have to get the value of from this particular graph. So, specifically saying, so all these graphs are obtained from USBR, so US department. So, all these design problems are given by them, and then we are converting into based upon our design. So, all these graph from this graph of H 0 by R s. and at a given pressure level. So, you have to take the calculate the value of Hs by H0. So, how you can do that? So, here suppose your value of again it is 1.3 and 1.4. So, for these values and the corresponding value here, so you can see between 1 and 1.02, 1, 2, 3, 4, 4 divisions are present. So, using interpolation you come to the conclusion that this Hs by H0 is in between one, this particular point is, if you divide this between these points as 4 equally spaced points. So, you find that Hs by H0 is nothing but around 1.0133. Now, you know the value of H0. So, you multiply with that. So, now Hs value comes as 3.04. Okay. And now, so this is from Hs value, and you have the value of H0 you know is which is 3 meter. So, this is H0 3 meter. So, you know the Hs value which is 3.04 from earlier calculation. So, this point between these two is Hs minus Ha is nothing but 4.04 meter or 4 centimeter. Now, the xy coordinate of the crest profile for the portion above the wear crest is given in the table, in the following table. So, the value of Hs by Rs is 1.41 now. So, for different value of Hs by Rs, so this table is given. So, between 1 and 2, so 1.4 lies between 1 and 2, and for different x, so this is at different P by Rs, the ratio between P is for 2. So, we assume our entire calculation was based on the ratio between P by Rs as 2. So, for different values of Hs by Rs, we interpolate for different crest profile, and then we plot this. So, at a crest elevation of 30 meter and at a different value of x and y, and Rs, the radius at the inlet is 2.15 meter was kept, and we can get the crest profile like this after interpolating these table values. So, once we obtain the crest profile, and now we determine the transition profile. So, this is the transition profile. So, crest profile was this, the top point panel. So, this design was completed. Now, the second part, the transition profile. The transition shape required to pass the 56 cubic, that was the design discharge, with an H0 of 3 meter above the crest. So, the water surface elevation was 30 meter and the surcharge head as 3 meters. So, total comes to be 33 meter, and using this equation which we already described in the design part. So, you plug the value of 56 cubic here and using this equation. So, this equation assume the total losses through transition are 0.1 times the Ha. So, using that, so once you plug the 56 value here, you get the value of R as 1.527 divided by Ha. The equation 1 is obtained. Now, for different shape radius, it can be computed for different elevation. So, the elevation of the section, if it is 30 meter, is given, and for different value of head you can obtain the different shape radius like this, and a tabular value can be obtained. Now, the next part is the determination of the minimum conduit diameter. So, first we assume a known conduit diameter, say 2.5 meter, which is standard. Since the diameter is 2.5 meter, the radius is half of that. So, this is the 1.25 meter is obtained like this, and this corresponds to, so we again plug into the basic equation. So, this equation here, so equation 1. So, in that way we can get the value of HA, where Q was kept as 56, and this is using the assumed radius, and which is the head is nothing but 2.22. Now, the throat location is 33 minus this 2.22. So, this comes to be 30.78 meter, which is nothing but we round it to 31 meter elevation. So, the assume the conduit length of 76 meter from throat transition to the outlet point. Now, we will take into care the frictional losses. Since the frictional losses are approximated assuming the conduit flows 75% of the entire length. So, here, so this part is considered. So, the discharge divided by, since it is 75% of the flow. So, this was plugged here considering the 75% of the flow, and these are assumed diameter. So, since the cross section is assumed as a circular, so this relation is nothing but pi by 4 d square. So, in this way we calculate the velocity. Once we obtain the velocity, then we will calculate the velocity head, which is nothing but h v is v square upon 2 g. This is the head loss due to the velocity. So, this note, this is a multiplication, and this one is the head loss due to the velocity head is comes out to be 11.8 meter. Now, since the pipe is 75% full, so from this graph, so this is the ratio between V by V full and for different depth. So, 75% full. So, you can take the point here, okay, and here. So, it is 75% full. So, corresponding Q by Q0 is around 0.70. So, this is the diameter at the inlet divided by the diameter at the outlet portion. So, d by d is a ratio is around 0.70, and your diameter is assumed as the inlet this is the outlet by inlet diameter. So, the inlet diameter is the bigger diameter or and a smaller diameter. So, this one is kept as d and this one is small d. As you remember, this is the complete cross section. So, this diameter is bigger. So, this one your capital D and this diameter is the small d. So, this ratio is given by this kind of graph. So, now, so small d, that is the diameter at the transition point, is a function of 0.702. So, here the diameter is 2.5. Now, you assume the Manning's roughness coefficient for naturalized flow as 0.014. Now, this is the this universal equation, the velocity of flow through open channel. So, using that, so you can get the value of S. So, V n square. So, this is done here, and since small d is the radius here. So, this is small r. So, this is the value of 1.75 by 2. So, this is 0.87. So, this slope is comes out to be 0.055. And now, this is the head loss due to friction is the length of the pipe and slope of the head slope due to friction, and this comes out to be 4.18. This is the head loss due to friction. Now, we apply the conservation of energy equation to check the outlet invert elevation. So, here the in elevation at throat is positive and the pressure head at the throat. So, this has to be negative. So, we are deducting this. The velocity head at the conduit, assuming the pipe is 75% full. So, you will have to deduct it because this is a head loss. The frictional losses at the conduit. So, this is also you have to deduct, and the depth at the outlet. So, you assume that this is a circular cross section. So, the depth at the outlet is nothing but that equation 0.072 D. So, the invert elevation, so throat elevation was 31 meter and a velocity head at throat. So, this was the invert elevation minus the 31 here, and why we are dividing it 1.1, because the HA was assumed to be as 0.1 of HA. So, considering all losses. So, that is why we are dividing by 1.1, and this is the velocity head, and this is the frictional head loss at the conduit, and this is the depth at the outlet given by this equation. So, this comes out to be 15.27. Now, the invert elevation was given in the design problem is 16 meter, which is very close to 15.27 meter. So, this in this case the design was accepted. So, the calculated invert elevation is very close to the given invert elevation of 16 meter. Now, a water surface profile through the conduit should be computed. So, in case if the calculated outlet invert elevation it comes lower than the established elevation. So, suppose our calculated invert elevation is comes in the problem is 15.27 meter, which is around 16 meter. We will consider the higher side is lower than the established elevation that is given in the problem. Suppose the established elevation is 20 feet or 18 meter, then the conduit diameter is to be increased. So, in that case you have to increase the diameter, say the assumed diameter was 2.5, now you increase the next higher size like 2.8 meter, and then repeat the calculation steps until the desired invert elevation is achieved. So, in this way the design problem goes. Thank you.